is I'll take this recording, I will send it to Dr. Casper, and he can do whatever with it that he wants. And that way he'll have an idea of what we're covering this week. I guess you guys took an exam last week. I do have those exams. I think what I'll do is give them to you at the end of class. He didn't tell me anything about going over them or anything like that, so I'm just going to basically give them to you. I haven't even looked at what it is anyway. But I'm sure once Dr. Casper comes back, if you have questions about those exams or anything you want to talk about, I'm sure he'll be able to help you. Lastly, I was dealing with a horrible cold last week, and it's bad enough that I'm now into the second week. I'm a little stuffed up. I feel fine, but if I sound a little off, that's all it is. So we'll take a break at some point to give myself a little bit of a break in the middle of class, but I'm definitely doing better than I was last week. So with that in mind, the topic of what Dr. Casper had wanted me to at least start with, I'm going to try to line up as best as I can with that, which is the topic of splitting fields. So I'm going to kind of try to number things, if I can, as closely to Hungerford's book as I am able. And section 11.4 of the book is about the topic of splitting fields. So I'm going to kind of partially use my own notes and then partially use some of his notes as well in order to discuss this. So what is the whole goal here? I know you guys have done, you've already talked quite a bit about field extension theory, and this is sort of combining that with the study of the roots of a polynomial. As you guys have known ever since grade school, one of the big things you like to do with equations is factor them and solve them. And that means finding roots of equations. And splitting fields are going to be very intertwined with that goal. So the goal is, if we are given some polynomial, I'll call it little f of x in capital F of x. Of course, capital F is a field, as I'm sure you're normally used to seeing. What we're hoping to do here, guys, is find an extension field. And Hungerford, as well as Dr. Casper's notes, seem to indicate that usually we would call that extension field K. So this is a field that contains capital F such that, so there's going to be two conditions here about this. We have a polynomial and we have a base field F, and we're hoping to find this extension field. And the first condition is that we would like for f of x to split over the extension field. So f of x splits over k. Now let me explain exactly what that means. What that means is that you can fully factor f of x down into a product of linear factors. So let me write that out actually as an expression here. So i.e. F of x should be somehow in the form of some coefficient in front, I'll call it c, times a product of linear factors. So we might have x minus u1 times x minus u2, and so on and so on. And then the last one might be something like x minus un, where all of these u sub i's are elements of k. And the C is going to be something from the base field F. So, but the point is that the roots are in this extension field K, right? All right, so that's the first thing. Now, of course, if you found a extension field K that allowed you to fully factor f of x like this, you could, of course, make K even larger, and the polynomial would still have the same acceptable factorization because all of these u's still live in any field that contains K. So I'm not trying to suggest that there's only one field K that can accomplish this, right? In fact, there could be many such fields. So, however, we're going to add a second condition now. So the second condition here, part B, is that K is as small as possible. Okay, so in other words, I want it to be at least as big as F. It has to be containing F, and it needs to be such that f of x really can be split up in this way. that it really splits in this way. So really what I mean here is that K is equal to the field, and now here I'm gonna rely on, you guys have to let me know if you haven't seen any of this notation, but if I want to extend a field by adjoining elements, right, typically that will be written like this. You take the base field F and you adjoin 1, 2, 3 up to, in this case, n additional elements. You can think of this as just a series of simple extensions. You started with the base field F. I always like to draw, I don't know if Dr. Casper likes to draw these kind of tower-like diagrams. So where you sort of adjoin an element to a base field, and then to that you can adjoin another element, which is effectively the same thing as having adjoined both of them. And you know, you can build this up as high as you want. It's just like some kind of a tower here. Okay, and so with this understanding, now we have not only managed to fully factor our polynomial f of x, we've kind of done it with the smallest extension field that we could do it with, right? Because if k didn't have all of these roots in it, you wouldn't have been able to factor it as this product of linear factors. So you really minimally are going to be required to add all of those elements in to the base field. And this is the smallest field, right? This is the smallest field that contains f and all of these individual roots. Okay, I'm hoping that I'm making sense so far. Now, there does come a question about whether this k is unique. You know, I say k is as small as possible. Well, in mathematical context, we often find that there's more than one sort of smallest object in a set. And you might wonder whether maybe there would have been some other way to create a splitting field, which is really what this k is going to be called, for this polynomial. Turns out that splitting fields, they are unique up to isomorphism. What this means is that if you had other potential ways to create k, where you've got f of x factored as a product of linear factors, any other way of creating this extension field would give you a field that's isomorphic to k. Okay. Have you guys talked about unique factorization domains? Right, so if your polynomial was not in a UFD, then maybe the roots, maybe you could refactor f using different roots besides u1 through un, and then you would have a different k for that situation, right? So you now have like apparently a second splitting field for that second factorization. So the point is that, I'll just make this as a remark, is that such k is unique up to isomorphism. And this is where I'm going to deviate from Dr. Casper's notes a little bit. He has an entire production of the proof of that result. And he may well want to show that to you next week. I'm not going to do it. I'm going to kind of take it as just a side remark for the time being, that this is actually more or less unique up to isomorphism. If there was a different extension field of f that we could factor f of x fully into a product of linear factors, that other extension field would have to be isomorphic to this one. So that's one of the results that we have. But if we're willing to accept that this is unique, because I'm going to have to, the proof of this isn't so much fun, and my deal with Dr. Casper is I'll sub for you, but I get to do the fun stuff. You have to come back next week and fill in all the technical details that are not so fun. So anyway, so we're going to make a definition then with that kind of understanding of what is a splitting field. So the unique field, so now I'm going to call it unique. The unique field K described above. Let me know if my handwriting needs to be bigger or if you're having any trouble reading anything here. But this extension field that we've just described above is called a splitting field. A splitting field of the polynomial. little f of x, which is in capital F of x. Okay, so I thought maybe we should do a few examples. Dr. Casper has some examples too, and his examples are more or less similar to mine. So let me go ahead and write down a few examples of splitting fields here. We can maybe work on this a little bit together. Let's suppose that we take f of x to be, so ex just means example. I'll be using that notation quite a lot. Let's suppose that we take f of x equal to, just x squared plus 1. And I'm going to view that as a polynomial in R of x. It's actually very important that the base field is clear, okay? Like you won't usually hear, so if somebody just says, oh, a splitting field for f of x is k, that's kind of sloppy, because they're not saying what is the base field that gives rise to that splitting field. And we'll see that almost immediately here with these examples. So we have to look at this polynomial and think about the roots of it. We set this equal to 0. What are the roots of this polynomial? Anybody? Plus and minus I, right? So in this case, what we would do is we would define our splitting field k to be the real numbers, and we would adjoin plus or minus I. Now I don't technically need to adjoin minus I, because once I've adjoined I, remember this thing has to be closed under addition, subtraction, multiplication, division, so you'll pick up that minus sign easily enough. And what is R adjoin I? Does anybody know what that simple extension is?
Complex numbers.
Complex numbers, exactly. So the splitting field of x squared plus 1 over R of x is C, okay? However, if we take that same polynomial again, I'm going to take x squared plus 1 again, but I'm going to view it as a polynomial in Q of x this time. And I'm going to ask, what is the splitting field for the polynomial over Q of x? And in this case, we approach it the same way. We adjoin the root, in this case I, to the base field. But since my base field was Q, this is Q of I instead of R of I. And Q of I is just Q of I. This is just, this doesn't have any simplification. It's just the set of A plus BI, where A and B are elements of Q. Does that make sense? So the splitting field of a polynomial, obviously it depends on the polynomial, but it also depends on what base field the polynomial was being considered to be built over. Okay, so that's a key point. Let's do another example. Start off with some relatively easy ones here. Let's do x squared minus 2, but let's view that over R of x. Go back to R of x again. Okay, so what are the roots of that polynomial? You set that equal to 0 and solve for x, you'll get plus and minus the square root of 2, okay? So my extension field that I need here is R with the square root of 2 adjoined to it, and actually that is equal to R. So because the square root of 2 is already part of R. So in this case, this polynomial already splits even over the field that it's considered a part of, or that its coefficients are considered a part of to begin with. So there's no extension needed here. It is already the splitting field. But of course, if we take that same polynomial one more time, and this time if I go back to looking at scalars that are rational, so I'm viewing it as a polynomial over Q, in this case my splitting field up to isomorphism is just Q adjoined the square root of 2. And so this is just A plus B radical 2, such that A and B are in Q. Okay, great. Let's do a couple more. Let's take something maybe a little more interesting here. How about we take a slightly higher degree polynomial? I've got x to the 4th minus 4x squared minus 5 down here in my notes. And again, I'm going to view this over Q. So this is a polynomial in Q of x. And this time we might not be able to immediately write down the answer without doing a little bit of work first. This is a 4th degree polynomial, so it will have 4 roots. but I've set this up so that they aren't just totally obvious. Does anybody have a suggestion how to try to get at the roots of this quartic polynomial?
Substitute x squared for, let's say, a.
Yeah, if we kind of think of this x squared as a variable in and of itself, then this is really just the square of that variable minus 4 times that variable minus 5, and it's a quadratic again. You can view this as kind of a quadratic of a quadratic. That's because there's no x cubed or x terms that we can kind of get away with that. So if you actually think about it, it does actually factor. At least initially, we can write it as a product of 2 quadratic equations, which would be x squared minus 5 times x squared plus 1. And once we've got it that far along, the quadratics can both be factored, and you can see what the roots are going to be. You'll have, obviously you see the plus and minus I again, but we also have plus and minus the square root of 5. So in this case, k would just be, starting from q, we have to adjoin I, and we have to adjoin the square root of 5 this time, okay? So that would be the splitting field. It's not quite a simple extension of q this time. It's a little bit larger extension. Okay, let's do one more. Come over here. I'm going to move this camera maybe so that it can pick up the board a little bit better. Okay, so let's try this one. How about f of x equals x cubed minus 1. I'm going to view this over q of x. Turns out that this is more interesting when we ask questions like this over q rather than over r. Because if you extend r, the only possible extension of r is going to be the complex number. So it's just a matter of whether the roots are imaginary or not as to what the splitting field is. So I find this type of base field of q to be a little bit more interesting here. So let's think about the roots of this one. Okay, does anybody know how to factor a cubic?
Take x minus 1.
X minus 1.
You're gonna have x squared.
X squared.
Plus, and then x.
I'll help you.
Yeah.
Plus x plus 1,
Yeah.
right? Everybody should know how to do this, by the way, right? When I attend the graduation and I sit down in the front row, like before somebody's quite ready to go across the stage to get their diploma, I usually tell them stop the music for just a minute. I have one last test to make sure there's not a terrible mistake being made here. So this could be it, right? Can you factor a cubed minus b cubed? Something to think about. Anyway, yeah. So this one is going to factor just like so. And in this case, we can get the roots. Obviously, we have 1 as a root from the first factor. The second factor is a quadratic. And so I'm going to go ahead and use the quadratic formula to get this one. This one does not factor so easily, so we actually could use the quadratic formula. -1 plus or minus 1 minus 4 all over 2. Okay, and that becomes -1 plus or minus the square root of 3 times I all over 2, okay? This pair of roots actually comes up a fair amount in the examples in the book. So the book actually will refer to omega. So this W is generally called omega, and it is 1 plus the square root of 3 times I all over 2. I don't know if this has come up in any of your examples before. The other root is the complex conjugate of omega, which would be -1 minus the square root of 3i all over 2. But I should actually point out that the conjugate of omega is actually also just omega squared. You could check that out if you wanted to. Actually, this one is worth pausing for a moment to think about. We're talking about the 3 cubed roots of 1 here, right? The roots of this equation are the cubed roots of 1, and there are 3 of them. And they will all be, if I look at the complex plane, they will all be spaced around the unit circle, basically equally spaced into three parts. So here's one, right? again, this is the real axis, this is the imaginary axis, just to have a visual of it, okay? Omega is over here somewhere, negative a half, plus the square root of 3 over 2 times I, right? So that's approximately right there. If we take the conjugate of omega, that means we're just flipping the imaginary part of the number. So that literally, visually, that just flips across the real axis. But it turns out that that is what omega squared would be as well. So you can view it as either omega or as omega squared. And so these are the 3 roots. So in this case, sorry, I'm gonna come back up here to write down the splitting field. The splitting field here would be to take Q and adjoin, I have to adjoin the roots. Well, 1 is already part of Q, I don't have to do anything for that. We do need to adjoin omega, right? And we technically also need to adjoin omega squared, but remember that we're making a simple field extension here, which will have to be closed under all operations, which means omega squared is already in here. So this is it. This is the whole thing. And by the way, this is an extension only of degree 2, because the minimal polynomial for omega is actually just this one. That sort of smallest irreducible polynomial for omega, it's just this quadratic. So what you've got is just a quadratic extension of Q here. And that becomes the splitting field for x cubed minus 1. Okay, so we've got a few nice examples here. Now, you might wonder, would it be possible, question, yeah.
Is there like sort of a natural analogy for just a general nth root of unity, for example, like the fourth root of unity and so on and so forth?
There is. We could generalize this, and in fact, I often do that when I teach 407. I'll show everybody this one, and then I'll maybe do one more of them in like a homework or a group work or something, and then I'll throw the big one on the test or something, like the 9th roots of unity or the 7th roots of unity or something like that. So yes, you can definitely generalize this idea. And if you're really interested in examples like this, you should think about taking Math 412, which is our complex variables, complex analysis course, where you'd really hammer this home carefully in a class like that. Another hand? Yeah.
So is the reason that the minimal polynomial is x squared plus x plus 1 is because by doing that work, you got omega, and that's really the only thing you made the splitting field with?
Correct, yeah, so omega satisfies this equation too, but this one's not irreducible. We can factor it like this and this. This one is irreducible.
Yeah.
Right, because, sorry, I should be more clear, it's irreducible over Q.
Yeah.
Because, if somehow this was reducible over Q, you'd have to be able to factor it into 2 linear factors, which would both have rational roots, and omega is not rational. Okay, so I know this is as far as I'm gonna be able to factor this thing, and whatever sort of the smallest degree polynomial is, monic polynomial, that's gonna be your irreducible polynomial for omega.
Thank you.
Yeah, good question. Okay, anything else so far? Oh, I'm having so much fun with this. I was so sad when they didn't give me the class, and then I thought, but still let Dr. Casper teach it for once, that I can have it back from him at some point in the future. I'm sure he's watching this. Anyway, yeah, so I do have a question. Like, would it be possible for somebody to hand us an f of x that we literally, it's as hard as stone. We can't factor it at all. Like, we can't get anywhere with it, we can't think of how to even parse, like here we sort of had to take baby steps and do it in 2 parts. First break it into quadratics and then go from there, right? Same thing here, we had to sort of do a partial factorization first and then go from there to get the roots of the remaining quadratic. But what if we can't even get it started? Like, what would happen if your f of x was just like totally unbreakable, unfactorable? It turns out that cannot happen. Every polynomial is going to be able, this goal over here that we started with is always achievable. We will always be able to find this splitting field. So they always exist. So this is going to be a little claim here. Now I'm going to write this down, that basically every polynomial, little f of x over capital F of x, will have a splitting field. In other words, we're talking about existence of a splitting field here. And to help us with that, I'm gonna actually prove this one because it's in Dr. Casper's notes and I figured he might like it if I do this. It kind of comes in two parts. I'm gonna start with what I'll phrase as a lemma here, which is the following statement. So let's let capital F be a field. And we'll take our little f of x in capital F of x again. And let's just assume that the degree of f is at least 1. Take a polynomial of degree at least 1. Then, okay, ultimately I want to fully factor f of x like we did here in this splitting expression. However, I'm gonna take baby steps on that, and I'm gonna hope that I can just factor out one linear factor that has one root of f of x as part of it. So which is kind of what I did right here. I have 3 roots, I sort of factored one of them out, and then looked at what I was left over with. Okay, so this is kind of the idea about how this result works. So then there exists a simple field extension this will be f of capital U, so we're gonna adjoin some element u here, of f of x with f of little u equals 0. This is a lemma. What it's saying is that if I take any polynomial over capital F, then what I can do is I can find a root, I'm gonna call it little u, I can find a root of little f in some suitable simple extension of, actually this should be a simple extension f of u of capital F. It's an extension of capital F, I'm sorry. So just a single element being adjoined to the base field. And so I'd like to start by proving that, and then we'll prove the bigger result that we can in fact always find a splitting field for every polynomial f of x, which is what these two conditions are. Maybe I should actually keep that left side up for a little longer. Let's erase this part just right here. Okay, am I making any kind of decent sense? Okay, perfect. I try. Okay. Okay, so let's talk about the proof here of that lemma. Start with the proof of this lemma here. The first thing we're going to do is we can write f of x as a product of irreducible polynomials. You know, you're in a unique factorization domain, you know, you can factor f of x down somehow. In particular, now it could be that f of x itself is already irreducible, in which case this product just consists of f of x alone. But in particular, f of x is going to be divisible by any one of these factors in this product, right? So f of x will be divisible by an irreducible polynomial, like any of those irreducible polynomials in that factorization. And let's just call the irreducible polynomial p of x. That should be pretty standard notation for that. Now, you guys have learned, I assume, that if you form the ideal generated by an irreducible polynomial over capital F of x, that is a maximal ideal. Does it sound familiar? Remember the theory of ideals with over polynomial rings, right? What are those maximal, all of those ideals are principal, generated by a single element. And which ones are maximal? They're the ones that are generated by an irreducible polynomial. So recall that this principal ideal, we would write it with parentheses around it, generated by P of X is a maximal ideal of capital F of X. This should probably takes us back a few chapters to some earlier material. And in particular, we can, whenever we have a maximal ideal, do you remember what happens when you take a ring, this is a ring, and you mod out by a maximal ideal? What does that always give you? A field, exactly. So if we form that field, I'm gonna call it K. This is going to be the K that we're going to be working towards here eventually. So this is F of X modded out by this principal ideal generated by F of X. This is a field. This is a field, and in fact, we can view it as a field extension of capital F itself. Okay. Right, so in particular, this is a quotient, a collection of cosets. And the coset representatives include all of the constants. So capital F, there's a copy of capital F sitting inside of K. So you can really view it as, you can view K as an extension of F in that way. You've probably already seen that. So what I'd like to note is that since P of X actually divides the F of X that we're starting with here, then that tells us that, you know, F of X is sort of congruent to 0 modulo P of X. Sort of congruent to 0 modulo P of X. And so now I'm going to, let's see, what does this lemma require me to do again? Let F be a field, take our polynomial. We have to show that there exists a simple extension, F of U, such that F of U is equal to 0. I've got an extension here, I don't know if it's simple or not, but I am now ready to show you what the U is, right? In this lemma, I have to produce a U for you. So I'm going to do that right now. I'm going to write down a U, and then we're going to stare at it for a minute and see if it makes sense. And the way the U is going to be written, U is going to live in this extension field. So it's going to look like a coset. So I'm going to write it as X plus the principal ideal generated by P of X. That is a coset that lives in the field K. Okay. And I claim that that guy is a root of little f. In other words, I claim that little f of U is 0. Let's check it out. So then f of little u, I can work this out and see what it is. So in other words, you're plugging u into the, so essentially you're taking f of this coset. You can sort of plug, I get a lot of parentheses around that. You're plugging the proposed root into f here, but because this is a field and it respects addition and multiplication and all of the polynomial operations, I can think of this as just f of x plus the principal ideal generated by P of X. And what is that? F of X, in the world of mod P of X, f of X is just the same thing as 0, basically. So this thing here, f of X plus this coset, is literally equal to 0 plus this coset. In other words, it's the 0 element of K. It is the 0 element of K. I'll denote it this way. So we plugged in U into our polynomial and we got 0. That means that U is a root of F, and we can therefore make this simple extension of F and have a root of our polynomial. So this is not as strong as saying we found a splitting field for our polynomial, but what we are saying is that we can take our polynomial and we can find a root of it. We can find a root in some appropriate extension field, and that is what K was defined to be. Okay, so this is basically all I have to say about that, I think. Yeah, that's the proof of that lemma. And with that in place, I'm gonna take a minute to erase, so if there's anything unclear about that proof, feel free to take a minute and ask me a question.
Dr. Ed, in the lemma, it mentions that we're using that F has degree. Is that just something that you need to mention at all in the proof, or?
It didn't really get used in the proof. You're acting like a pure mathematician. There's an assumption in this statement, and it was never mentioned in the proof. There's gotta be something wrong with that. Well, if the polynomial had degree 0, this polynomial would not have to have any roots at all. So this is really only a statement for polynomials of degree at least 1. And if it had degree 0, we wouldn't be expressing it as a product of irreducible polynomials, even from the get-go. So it's a real good point. It's essentially a technicality. If your polynomial is a constant polynomial, there won't be any roots. And so the idea of trying to split your polynomial using the roots suddenly becomes pretty uninteresting. Yeah. Okay, well, with that, I am ready to now state the bigger result, which is, Dr. Casper has a nice name for this, which I didn't have in my version of this, simple field extension theorem. And for those of you following along with the book, I think in the book, this is theorem 11.13. So I'll add that for you in case that might be helpful. And so now we're gonna basically state that, yeah, every polynomial does have a splitting field. We've already remarked that this splitting field will be unique up to isomorphism. And now I have to just convince you that it even exists in the first place. And that's really what this theorem is going to say. So here we go. Let's let F be a field. And suppose that little f of x is an element of capital F of x, all right, of degree n. So let's get really specific here that we have a polynomial of degree n in our hands. And n is going to be greater than 0 again, so constant polynomials are not under consideration right now. Then there exists a splitting field. There exists a splitting field K of f of x. So every polynomial can successfully be carried out under this goal. We'll be able to take any polynomial and fully split it down. And actually, there's a little bit of a bonus to this. Not only will we be able to find a splitting field, we can say something about how big it is. A question, yeah.
Wait, splitting field of K of F, not F of X, or?
Splitting field K of f of x.
Oh, yeah.
So just if we take our polynomial f of x, K will be that splitting field of that polynomial.
Do we need to note the base field over?
It's kind of just stated here. So the f is the base field here. So you're technically right. So we could add over f. That make you happier? Okay, good. So we could make the splitting field K of little f of x over f. And there's a little bonus that this result has that I can get easily with the proof. So I'm going to go ahead and add it to the conclusion here, which is we can talk about how big that splitting field is. And I know you've looked at this dimension. If I think of K as a vector space over F, there'll be some dimension there. It turns out that that dimension is less than or equal to n factorial. Interesting, isn't it? So we'll get a little bit of combinatorics in here. Not that I'm trying to plug my class this fall, but I do like to teach that class. So we'll get a little bit of that going. And this is going to be proved by induction on N. So we'll be able to do the proof using induction on N. I'm gonna kind of show you how that works. So proof induction on N. That's the general approach to this result. And so as we know, we start with a base case, right? So the base case would be N equals 1. That's the smallest case that we have to think about. In this case, we can write our polynomial f of x as just a degree 1 polynomial, right? So we can write it as cx plus d, where c and d are in f, and specifically c should be non-zero in order for this to be a degree 1 polynomial. Okay? And in this case, basically it's already factored. I mean, you've got one root. The only root of f is, you just set that equal to 0 and solve for x. It's going to be negative d over c, basically. And that exists in f because f itself is a field. It's already got all the elements inside of it, including closure under division. So we'll certainly have that in there as well. And so what is our splitting field? We take f and we adjoin negative d over c to it. But since negative d over c is already in f, that is just f. So there's your splitting field that, what are we trying to prove? There exists a splitting field, K. Here it is, it's just itself, it's just the base field itself. And obviously the dimension of K over F is, in this case, since K is equal to F, we can literally just plug in F where we see K, and that's just 1. And 1 is less than or equal to 1 factorial. So that's the base case right there. Okay, so let's get on to the step, the induction step of the bigger part of the proof, so to speak. Let's assume that this theorem is already true for polynomials up to a certain degree. And then what we're going to try to do is push it 1 degree higher. Okay, so let's assume the result is true for, I'm try and do it with using his exact notes here. Polynomials of degree less than or equal to n. And then what I'm going to do is I'm going to take a new polynomial now, which is little f of x again, right? I'll take a new polynomial, little f of x, that has degree n plus 1. So the degree of f of x is going to be n plus 1 now, like that. So this is how the induction gets started. And what I'm going to do first, guys, is use my lemma, which tells me that I can find a simple extension of f that at least will have a root of my f of x. Okay, so let's do this. So by the lemma that we just did a few moments ago, so if we take advantage of that lemma that we already have in front of us, we can find a root u of f of x. So we can find a root of that polynomial f of x and write, what I'm going to do then is I'm going to write my f of x as x minus u times some other polynomial g of x. This is the key step, where the degree of g of x is actually n. So f of x had degree n plus 1. I'm factoring out this linear factor x minus u. And the remaining degree of g of x is only n, and I'll be able now to use the induction assumption on g. That's how the proof basically works. I should point out that g of x, I do want to be clear, g of x might not be in f of x. Because as soon as keep in mind that this u, this root here, is not necessarily in the base field. In fact, our lemma doesn't guarantee us that at all. It just says that there's some extension of the base field that has that root in it. So let's just be clear that this g of x isn't really in f of x, it would be in f of u of x. Just to be clear, what is the base field there? It would have to be f of u of x. But that's okay, because I can still apply this induction assumption to this polynomial g of x based only on its degree. The induction is being done on n. So far, so good. Okay, so that's what we're gonna do. We're gonna use the induction. So by induction, there exists a splitting field K of g of x over f of u. So this, in this context, the base field is already this extended version of f, which is f of u. So we have that splitting field for g of x with the degree of k over f of u less than or equal to n factorial. So that's the induction assumption here. So k is my splitting field over f of u, and by assumption, we have a polynomial of degree n, so this becomes n factorial right here. So if we use the field k, we can fully factor g of x into a product of linear factors. And tacking that along with the original linear factor x minus u, which requires me to have u, of course u is already part of k anyway, because this field is inside of this field. That will allow us to fully factor the original f of x. So in other words, f of x can be fully factored in k. Right, so let's just write that down. So thus, k is a splitting field for little f of x over capital F. We can totally split out the g of x, and then we will have a factorization of f of x as well. And remember that k includes u. So putting x minus u here is perfectly legal over k. And then these roots in g of x, they're also going to be in k because k is a splitting field for that. And let's just check something here, guys. What can we say about the dimension of k over f here? We know any nice theorems might help us at this particular moment?
Is equal to the dimension of a extended from f u times the extension of the u from f.
Exactly, guys. I love this theorem. When I teach 407, I go hog wild on this theorem. I do so much with it. I call it the tower theorem. It's like a tower of field extensions. So it's a very nice result. If the individual dimensions are finite, so the dimension of f of u over u, and then the dimension of k over f of u, if they're both finite, then the dimension of the large extension going all the way from k above f is just the product of those two. And we already know that this first one is less than or equal to n factorial. And the dimension of f of u over f is how much? Well, it's the degree of the minimal polynomial for u over f. But the minimal polynomial for u was a root of f of x, right? And f of x, so the minimal polynomial for u has degree at most, whatever the degree of f of x was, which is n plus one. So I can put n plus one here, and now we get our nice little combinatorics arithmetic going on. This is n plus one factorial, which is what our splitting field extension theorem says. So really nice result that we prove here by induction. Awesome. What do you guys think? Does it make some sense? I want to take a 10-minute break just before I do that, just to recap what have we said so far today. Given any polynomial over a base field, right, we can find some extension field of it over which the polynomial will split fully as a product of linear factors, right? And that splitting field will be unique up to isomorphism, but we now know that it exists. The splitting field extension theorem shows that it exists always. And its dimension isn't too big. It isn't too big. So, and we've seen a few examples of it. So I'm feeling pretty good. I'm feeling pretty good about this. Now, one thing that algebraists are always interested in are, of course, the roots of polynomials and how they behave under various types of functions. So after we take a 10-minute break, which I like to do in the middle of this is a 2-hour class, right? In the middle of a 2-hour class, I can't go that long. So let's take a 10-minute break. When we come back, I'm going to talk about permutations of these roots and associating a group of permutations to the roots of a polynomial, which is a beautiful connection. Did you guys do some group theory in this class?
Yeah.
It's a beautiful connection between group theory and the field extension theory that we've just been talking about right here. It's pretty neat. But let's take 10 minutes, about 5 minutes after 5, I'll pick things up again, but give you guys a chance to stretch your legs if you'd like, grab some fresh air, and we'll be back with you.
After never gives a break, so thank you.
Oh, really? Oh, okay. I can't go that long, I'm too old.
Yeah. I saw that, yeah. But in the pictures, so it's just like. Somebody. Yeah. That's fine. Yeah, Portland is kind of an action right now, we're on the. Like, manifolds and. We're almost there, it's in the last year, or last two. Yeah, it's not much strong. Analysis is definitely the worst stat, for sure. That's cool. What is- Oh. It's fine. It's like a nice one. It's really good. Oh, okay. He's really good. I mean, it's really hard, but I mean, yeah, like, or I think the two of quality, right? The material that, it varies. Some of it really some quality that you have, but I have to think, what is it? It's like, but no, these really chill top stuff. They don't help you with like starting.
Already,
Oh, yeah, yeah.
we're kind of in the hall here. Are some of you guys graduating this semester? Yeah, just in time. I got the email this morning. Did you guys get an email from the parking services? Yeah.
Yes.
They're gonna start
24 hours.
charging us on the weekend. I've been here for 23 years. They never did that. Oh my gosh, I'm so mad. It's usually like Friday at 5. It's like, oh, I can park anywhere. All the way until Monday morning. But I guess in the fall, not so much. They must be getting tired of like the entire city of Fullerton using their lot for basically 2.5 days every weekend. As a free parking lot, so they're gonna start charging people in August, so it's something to get used to, I guess. Anyway, let's talk about more pleasant things than parking. Yeah, I have not talked about everything in the chapter about field extension theory that I'm sure Dr. Casper would like to. But again, I'm kind of modifying things a little bit to sort of line up with sort of the way I think about this material. And the way I usually do it is I try to get some motivation for some of the rest of what's in that chapter by moving to the next chapter first. Because once we get a little ways into this chapter 12, we realize there's some concepts that we need to introduce to help us do chapter 12 a little bit better. So I asked Dr. Casper, he said I have his permission to go ahead if I want to and talk about what I think is really the climax of this class. I always like teaching classes where you're sort of building to some sort of grand finale where you're bringing everything together. It's very much a culminating portion of the semester, and here we are the last 3 weeks. It's about time that we get to it. Galois theory is named after a mathematician. I don't even know if I can call him that. He only lived to be 21 years old. It's amazing how much he accomplished in his very short life. This entire theory could easily form the backbone of an entire course. Certainly at a graduate level, you could spend a semester or more just getting the ins and outs of this theory. It's called Galois theory. So that's how it's pronounced. And let me try to give you a little sense of this theory today. And certainly on Wednesday, we'll get much more into this. But of course, it's always helpful to have a problem kind of underlying the theory, and to kind of get the lay of the land a little bit. So I'd like to think about the following problem. If we are given, let's say, f of x in capital F of x, as always, so capital F is our base field, we take a polynomial over that field. Does there exist? So earlier today, we were talking about the roots of this polynomial, the fact that there will always be a splitting field in which those roots live. But I want to get a little bit greedy here and ask, could we actually always find a formula for the roots themselves? Okay, so what could be better than actually knowing formulas for those roots? So does there exist a formula, a single formula, a closed form formula for the roots of this polynomial? Of course, those roots, as we've already discussed, would exist in some splitting field. So in some splitting field K over capital F. So it's a question, it's a problem. Could we be able to do this? Now, you guys already know the answer to this in at least one very familiar setting, which would be, are there certain polynomials that you always know how to find the roots of?
Quadratics.
Quadratics, exactly, right? Quadratics over Q, for example, or over R or over C. So if the degree of f of x is 2, let's just say that we're over Q. So let's say take the base field here to be Q. In this case, then for the polynomial f of x equals ax squared plus bx plus c, if we take just that nice quadratic equation, this would be where a is not equal to 0, right? Then we do have a formula for the roots. As you all know, negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, there would be some fields over which this would not make sense. For example, Z2. If the field was Z2, then in that realm, 2 is the same as 0, and now you're dividing by 0 here. So we wouldn't, we can't really apply this formula in every universe that we could be considering, but that's the quadratic formula that everybody knows about. Now, it turns out that in the 16th century, just give you a brief little history of this. I'm not going to make this too long, but just briefly. In the 16th century, formulas for cubics and quartics were discovered. They're not nearly as nice. You probably don't have them memorized on a regular basis like this one, but they do exist. So formulas for roots of cubics / quartics were discovered. And again, I'm thinking of the same base field of Q here. Okay, so third degree and fourth degree polynomials, we had roots that were discovered. However, in the 19th century, so in the 1800s, and I'm sorry I don't have exact years for you on this, Galois showed, so this is one of the things that's part of the famous theory that is named after him. He showed that there is no formula. There is no formula for the roots of a quintic So that would be degree of f of x equals 5. There is no general formula for the roots of a quintic, I'll say in general. It's called the insolvability of the quintic. If you want to really read up about this online, if you type that phrase in, insolvability, put that here, insolvability of the quintic. If you look that up, you'll find a whole lot of material about this. This is a famous topic in abstract algebra. Certainly, it is well correlated with the Galois theory that we're talking about right here. So, of course, if we're talking about no formulas for the roots of a quintic, then any polynomial of even higher degree than that is also going to be problematic. Degree 6, degree 7, degree 8, we're not going to have roots or formulas for the roots of all of those either. Okay, so those are insolvable. So a couple of questions maybe come up at this point, based on that little history, quick review. And so let me state those here. The first one is, why is there no formula for the roots of a quintic? So can we prove that? So why is there no general formula? In some special cases, like if I give you this, here's a quintic, right? Earlier today, we talked about the cubed roots of unity, the 1, the omega, and the omega squared, and somebody asked me, well, could you do that for a higher power here? You can. Something like this, we could obviously find the roots in around 5 equally spaced points around the complex circle. So I'm not saying that there's no polynomials for which you couldn't have formulas for the roots, but why is there no general formula for the roots of f of x when the degree of f of x is at least 5? So that would be one question, is what is the reason that we can't do this? In other words, what did Galois really manage to discover? And then the follow-up to that, though, is, as I said, sometimes we will be able to find the roots of the polynomial. So for which f of x, for which polynomials, can we find such a formula? And the idea is that to each polynomial, we can associate a group to that polynomial. That's what I'm going to be explaining this week. We can associate a group to a polynomial, and depending on the properties of that group, that will dictate whether that polynomial will exhibit such a formula or not. It's going to depend on the group, and there's actually the definition of a solvable group versus an insolvable group. Something's not solvable. So anyway, the idea here, I'll just go ahead and express that for now. We'll get into the details of this a little bit later, but the idea is, given this polynomial f of x over capital F of x, okay, so if we take this polynomial, find its splitting field, which we're calling K. We imagine there is some splitting field, and associate a group to the extension K over F. I'll just write it like this with a K with a slash F on it, to that extension, and study this group. This group is generally written gal of K over F. So there will be a group, and that's going to be the notation that is consistent with Hungerford's way of writing this group. So that's going to be the idea. Okay. So what I think I'll be able to at least explain, I'm sorry, it's 12.1. But I think I'll at least be able to get an explanation of today. This is just kind of the background, the introduction to where we're headed with this. I think by the end of today, I should be able to define that Galois group for you, and how that works. There's a little bit of background that we need, so I'm gonna start with that, and this will take me back to Dr. Casper's notes again, which will be good. Try to cover what he has laid out here. We're going to need to talk about what are called F homomorphisms of an extension field. So if we have this extension field K over F, of course, we've got this concept of homomorphisms. You've seen that for groups, you've seen it for rings, you've seen it for fields. And we even have it for, so we can talk about homomorphisms of from K to L, right? But there'll be some base field here that's inside of both of those extension fields, and an F homomorphism has to preserve that base field. So let's write down the definition of this here to kind of get this section started, okay? So I can't define the Galois group quite yet. I have to kind of get a little background first. So here it is. Let's let F be a field. Kind of goes without saying, but I'll write it down anyway. Let F be a field, and K and L field extensions of F. So we take a couple of field extensions of F, like so. Then what I'm gonna define for you guys right here is a homomorphism. I'm gonna underline this word here, homomorphism of field extensions. Okay, so this is what we're gonna talk about. Homomorphisms of field extensions is an F linear, it is an F linear ring homomorphism. So it's a ring homomorphism. Let's just remember, ring homomorphisms have to respect addition and multiplication, which are the two operations in a ring. In addition to that, this homomorphism is also going to have to respect scalars, which are coming from the base field F. So those scalars have to be kind of like in a vector space linear transformation context. If you have scalars that are being transformed under a linear transformation, you have to be able to factor them out of that linear transformation. So basically, these F linear ring homomorphisms respect everything. They respect addition, they respect subtraction, they respect multiplication, they respect scalars from the base field, exactly as you would expect. I'm going to call this sigma. And sigma goes from K to L. And that's the whole definition. A homomorphism of field extensions is an F linear ring homomorphism, sigma from K to L. But let me elaborate and just explain what does it actually mean. Let's write down the actual equations here so you can see them in front of you. I think that would be the best way to do this. So that is, there's actually sort of three properties here that we would want to list. One is that, well, sigma of x plus y should equal sigma of x plus sigma of y. This would be for all x and y in K, right? And then secondly, sigma of x times y should equal sigma of x times sigma of y, again, for all x and y in K. And then thirdly, sigma of a constant. Okay, so if we have a constant c, that should just be equal to c for all c in the base field capital F. So that's just for the elements of the base field. So when I say that I have an F linear ring homomorphism, what I mean is I have a homomorphism of rings, so it respects addition and multiplication, which are the ring operations. And the F part of it, the F linear part of it, is what item C addresses. Sigma fixes every element of the base field. Okay, that's the idea. And I should add here that if sigma is also a bijection, Okay, so that's also possible. Then we call sigma. What do you suppose we're gonna call sigma in that case? If it's a homomorphism that's also a bijection, that's better known as a isomorphism, exactly. So sigma, we call sigma an F isomorphism. Or it's an F linear isomorphism. I'm just gonna write F isomorphism. Okay, so that's basically what it is. It's an isomorphism from K to L in that case. So in this case, K would be isomorphic to L with sigma serving as that isomorphism explicitly. Okay, so that's the idea. As a little remark, so that's kind of a long definition. But the remark here is that this just means that you can form sort of linear combinations of elements that are expressed using K and L and F, and sigma will respect those linear combinations. So what I would say is for all A and B from the base field F, and for all, let's say, X and Y from the extension field K, then sigma, if it's a F homomorphism, then sigma of AX plus BY should be the same thing as, well, let's just break it down. Sigma of AX plus sigma of BY, because it respects addition. And then it also respects multiplication. So this is sigma of A times sigma of X plus sigma of B times sigma of Y. But the A and the B are from the base field F, and the property there is that anything from the base field is just fixed by sigma. So this just becomes A times sigma of X plus B times sigma of Y. Just like so. Okay, this is kind of what you would expect out of a linear transformation, right? Scalars can be pulled, you have a linear transformation and you transform it, you can pull the scalars out and split up the plus signs. Right, so that should be something kind of familiar even from linear algebra background. Okay, so we're gonna look at a lot of examples of these F homomorphisms, and in particular, we're really gonna be interested in the F isomorphisms. But we're also going to be even more interested in the case when the K and the L are the same. Okay, and I think I should probably add that as well to the definition here. So maybe oh, sorry, I just moved my camera over here. Let's just put it over here. We're gonna talk about the special case when K equals L. And in that case, it's called, instead of calling it an isomorphism, it's usually called an automorphism. Okay, so that's another word that's kind of in the same type of definition here. But let me just add that as well. So definition. And F isomorphism from K to itself, right? So this would be, sigma going from K to itself, and it's an isomorphism. And it respects F, it respects the scalars. This is an F automorphism. Okay, you might wonder, well, what am I gonna call it if the K is the same as L, but it's only a homomorphism? Well, that's a whole other word, that's called an endomorphism. So they're like all these different words, we don't really need all of them. This is really the most important one. This is really gonna end up being the most important one in terms of defining the Galois group that's associated with a field extension. Okay, so I like to draw pictures of this stuff to help me visualize this. So maybe you have K here, and I'm gonna put another copy of K here, and I have my sigma. And inside of K, we have the base field F here, right? So just put two copies of the same picture essentially, just to kind of see them side by side here. And we're talking about isomorphisms from K to itself, but everything that's within F gets directly fixed. So this function, which I'm now gonna use some arrows to visually represent, this function literally just goes straight across. Anytime I have an element little c, it ends up being fixed at little c again. Now, the elements that are outside of F can be, actually moved to a new places. It's still gonna be an isomorphism, so it still respects addition, multiplication, respects scalars, and it's a bijection, but it doesn't have to fix anything that's outside of F. That's kind of in my mind, I often think about an F automorphism kind of in this way that I've kind of shown you here. Okay. Maybe we should write an example down of what one of these things looks like. There's easy examples of F homomorphisms and F isomorphisms and so on. But let's just do one here. Let's take F to be the real number. This is probably the most famous one that you would ever think about. Let's just take the real numbers out of the complex numbers. And so at the moment, by the way, guys, I don't have a polynomial in my hands at this moment. I'm coming back to that. Right now, I simply have a field extension, okay? So there's no polynomial going on here, but I take my base field, I take my extension field, and I'm going to define sigma from K to K via, well, if I want to plug in a complex number A plus BI, like so, I have to imagine spitting out a complex number, and the most famous formula that I can imagine that you could make this work with is complex conjugation. So we replace A plus BI with A minus BI. In other words, that is, if we take just Z, if I just kind of represent the complex number as Z, then what I'm spitting out on this side is just Z bar, which is the notation for the conjugate of Z. And if you write it in this way, it's even more obvious that it respects addition, respects multiplication without having to, if you want to verify the properties A, B, and C for this function, it's a little more long-winded to do it with the A plus BI version as opposed to the Z version. So we could easily check them, but see, it's easier to check that sigma is an R automorphism. This is what I'm trying to do. It's just so easy to do it if I use the sort of the more compressed notation. Because if I have, this is property A over there, if I take let's say Z1 plus Z2, then the formula for sigma is that you just conjugate whatever you plugged into sigma. The complex conjugation respects addition, so you can just break this into Z1 bar plus Z2 bar. And that's just sigma of Z1, right? This is just sigma of Z1 plus sigma of Z2. Sorry, it's getting a little bit tight there on my space. If you don't like that proof, because it's kind of hiding the details, you can always go back to the A plus BI version and just check it there. It's not very surprising what's going to happen. So I think I'll just leave it in this form. We still have to check, for part B, similarly, sigma of, let's say, Z1, Z2. Again, Z1 and Z2, these are going to be elements of K. These are elements of K. The formula tells me to put a bar on top of whatever I plugged in there. And again, another nice property of complex numbers with conjugates is that they can be split up under multiplication. And so you just get sigma of Z1 times sigma of Z2. That's easy enough. And finally, for part C, if I just have only a real number that's being plugged in, which we could call A, then when I take A bar, well, that's just A again. This would be A as a real number. So that checks that you have a homomorphism. And then it's clear, can I say it's clear in this class? I was gonna say, it's clear that this is a bijection, right? This function will be one-to-one and onto, okay, so easy, let's just say easy to see. I won't use the word easy to see that sigma is a bijection. So it's a bijection, it respects everything, so it is an R automorphism. Okay. So that is one example. Can anybody think of another one? Just in general, a nice example? Or one that would have to be true always? Something that sends an element to itself, right? In other words, the identity mapping. That's always gonna be there. That's a great example, right? So for any, this is another example, for any extension that goes from F up to K, it doesn't even matter what K is or what F is, doesn't matter, then I'll just call it ID for identity. The identity function from K to itself given by identity of X equals X for all X in K. This is clearly an F automorphism. Yeah, that's like the easiest example that you could have. That is clearly an F automorphism. Not even a problem. Okay. Well, we're gonna see many others. I've given you kind of the trivial one and then probably the most famous one that's not trivial here. There are, of course, many others, and we'll see them coming up as we proceed through this exposition about Galois theory here. Are there any questions so far? Am I still making sense an hour and a half later? Hope so. Okay. If so, I am ready, as I thought I might get to it today. I am actually going to be able to tell you what the Galois group of a field extension is. This is the basic core of Galois theory, and it helps address that question I posed at the beginning about whether there's formulas for the roots of polynomials in that extension field. So let's make a definition. This is a pretty important definition here, guys. So I'm definitely hoping everybody's gonna feel good about this. The set of all F automorphisms of K is called the Galois group of K over F. And this would be written, I kind of hinted at this earlier, but now we'll get it into the formal notes here. Gal of K with a subscript of F on it. That is the notation for the set of all of those F automorphisms. Okay, well, I've defined it as because I've defined it as a Galois group, that doesn't make it a group, just because I called it that. So we have to have a theorem, don't we? We have to have a theorem that sort of says, well, actually, this is a group. Okay, so that your choice of terminology here is a good one. Okay, so the very first theorem, right, in this chapter is going to put us to ease about that. So the first theorem, 12.1 here, just says that gal of K over F as defined above, forms a group if we have a group, we have to have an operation in that group. Well, what do you think the operation would be if the objects of the group are these F automorphisms? Yeah, composition, exactly. So this would be forms a group under composition. It's going to form a group under composition. So I'm going to prove this. It's remarkably easy to prove this, actually. You would think, oh gosh, it's gonna be a lot of work to prove that it's a group. A group has a bunch of axioms. What is it? Does anybody remember this from, probably you learned about this at the start of the semester? We have to have a closure of the operation. A group always has to have an identity element. Gee, I wonder what it could be. Let's see, we have to have inverses for everything, and then there's associativity, right? So four primary axioms. Let's just kind of jump through these fairly quickly. So I'm going to start with a closure under composition. I'll use a little circle for composition if that's okay. It's sort of the normal notation for composition. And the way this is going to work is we're going to start with two elements of this gal of K over F. I'll call them sigma and tau. Okay. These are elements of gal of K over F. Just means that all that means is that they are both F automorphisms of K, right? So that's all that we know. So then, for one thing, they're bijections, and they respect all the multiplication, addition, and scalars. Well, when you compose two bijections together, of course, just basic set theory, you would have learned that the composition of bijections is still a bijection. So sigma composed with tau is still a bijection. It's also still a homomorphism. And fixes every, I'll call it C from the base field. Maybe, it doesn't hurt to kind of, since I've still got it on the board over here, I mean, just imagine that you put one more copy of K here, and you make a tau right here, right? So your F is here, right? Same thing, and remember that everything that's down here is just going straight across. And F automorphism is fixing everything from C. Up here, you don't know what's going on exactly, but whatever. So you're composing means you're sort of starting from here and you're pushing through sigma and then tau. And so what you can see is that the base field is obviously still getting fixed, right? It's still a bijection because each individual piece is a bijection, and it is going to be a homomorphism as well. So there's nothing really actually surprising that goes on there. All of that can be pretty easily convinced. You can convince yourself pretty easily that thus sigma composed with tau is still in gal of K over F. I actually realize that something's a little bit backwards here. When I do sigma composed with tau, that usually means you're doing tau first and then sigma. So I've kind of got these mislabeled relative to that comment, but you get the idea, right? You get the idea. I could change this to tau composed with sigma. It doesn't really matter. Let's see, identity element. We talked about that already. That is just going to be this ID example that we already put up here. So the ID right here, which is in gal of K over F, is an identity element. Not to brush over that too quickly. Remember, an identity element is one that when you multiply it by anything else, just leaves that other thing alone. Well, if you took this function and composed it on either side with some other sigma, then the effect on x would be whatever sigma of x is, right? So that's pretty reasonable. Inverses, Gotta talk about inverses here for a moment. How is that going to work? Well, given some sigma in gal of K over F. So this is an isomorphism from K to itself that fixes F, right? Can't I just take all of these arrows and just turn them absolutely around? And that's the function that sort of inverts the original sigma. So that's gonna exist in this group as well. So we have, it's almost just clear again, and we have that the inverse of sigma. And by that inverse, I'm referring to the inverse of this as a bijection. So anytime you have a bijection from one set to another, you can always form an inverse by just turning those arrows around. But in this case, when you do that, you actually just get another F automorphism again, just going in the other direction. So this is an element of gal of K over F again. And so I'm kind of just stating it. Yeah, I don't know that I'm really proving anything. They're not saying much more than, it's closed under inverses. Okay, so take my word for it. Associativity. Because we're talking about compositions of functions, that's always true. Functions are always composition of functions is always associative. So this is just comes for free automatically. So again, I'm just going to kind of state it. Compositions of functions are always, in any context, whether it's F automorphisms or something else, are always associative. That's certainly true. That's certainly going to be true. Okay, so we have a group. We have a group if we collect up all of the F automorphisms of K. So we have one field and then we have a field containing it. We have a group. I will tell you, for example, that do I still have my? I lost my first example of the complex conjugation. Turns out there are only two automorphisms of C that fix R. The identity and complex conjugation. That's it. You cannot possibly do it any other way. And because of that, the Galois group of C over R is a group of size 2, because there's only two automorphisms in there, and the only group I know of size 2 is Z2, up to isomorphism. So we can start classifying the isomorphism types of these Galois groups. By the way, the reason for that, we go till 5:50, is that right? Okay, so I have time to state one more result. I probably won't prove this today, but we'll prove it on Thursday. It's not hard to prove. But this next result is really the core of, or it's really what makes Galois theory work, and it makes it so beautiful, which is that these F automorphisms, these F automorphisms of K that are forming this Galois group, if you come along with a polynomial, I'm going to bring the polynomial back in front of you again, and you look at what all the roots of that polynomial are, let's say they all exist in K somewhere. Any one of your F automorphisms of K will have to map a root of your polynomial to a root of your polynomial. It must send roots to roots. I cannot overemphasize the importance of this result. Let me state it, and then we'll prove it next time, but I will also really try to hammer home why this is so important. So again, in the book, this is theorem 12.2. Let's just get this down at least for today. Let K be an extension field of capital F. And now I'm going to come back in here with the polynomial, little f of x and capital F of x. If U, which is an element of K, is a root of little f of x, we start with a root of our polynomial, and sigma is in this Galois group of K over F. So if we grab one of our F automorphisms, then sigma of u, so we apply sigma to u, which is something from the extension field K, is still a root of f of x. It still has to be a root of f of x. In other words, sigma, just in words, sigma sends roots to roots. And now maybe you understand why I'm calling my F automorphisms sigmas. Because if it sends roots to roots, and if we're talking about a bijection, then we're talking about a permutation of the roots. Do you remember the symmetric group? It's like the most famous group of all, right? I love that group. The symmetric group is the collection of permutations of a set. Well, what we're gonna be doing here, guys, is we're gonna be permuting the roots of our polynomial, however many of them there are. And each one of these sigmas can be thought of really as belonging to like a symmetric group. That's why I'm using that notation, because I assume you probably used this notation, talk about those kind of elements. So guys, just as a quick example, and then we'll call it a day. I am going to take a base field of R. I want to calculate one Galois group today. I can't get out of here without doing that. So let's take this thing here, and the question I might want to ask is, what is gal of C over R? What is that like isomorphic to? So just do one quick example. So I claim we can already get the answer, and that's because I am allowed to come along with any polynomial that I want to pull out of the sky. And the polynomial that I'm going to pull out of the sky right now, and I'm going to do this kind of quickly just because we're running a little bit short on time, but I'm going to work with the polynomial x squared plus 1. And what I know about that polynomial is that its roots are plus and minus I. And so if I have any sigma, if sigma is in the Galois group of C over R, then sigma has to, of course, map I somewhere. But we now know, if you believe the theorem, sigma must send roots to roots. So in this case, sigma of I has to either send it to itself, or it has to send it to the other root. The only other root we have is negative I. Now, if sigma does this, if sigma fixes I, then what is sigma of anything? Now let's remember, sigma busts apart. You can split up the plus sign. Sigma of A is A, sigma of B is B, sigma of I is I. My friends, this is just your identity element in this case. What about in this case? Well, here, if I do sigma of A plus BI, again, sigma of A is A, sigma of B is B, but sigma of I is negative I. These are the only two sigmas that you can make. There can't be any other sigmas, and so this is a group of size 2, right? So gal C over R is a group of size 2, and we all know from our background in group theory that there is only one isomorphism type for a group of size 2, which is actually Z2 itself. Right. And actually, if you composed the complex conjugation with itself, if you did it twice, you'd get back to the identity. It's an element of order 2. So there's a group structure there, which is confirmed by this group, by this theorem. And what we have to do on Wednesday, I can't wait to come back again. We have to do more examples of calculating these Galois groups. I'm going to prove this theorem for you, and a whole bunch of other fun things. So So I'm gonna leave it at that for now. I need to give you back your exams, I think, and then I'll let you guys go for today. Are there any questions? Oh, this is good stuff. I love it. I love it. Okay, now I know some of you, Bobby. And is Kevin? And Emily, gotcha. Francisco. Brady Brian. Okay, Brian is Weston. That's you, Weston. Thank you. Jean. Jean's not here, Kiana. And Chris. And that. Oh,
Maria. I already have mine.
oh, okay. I
Yeah,
was.
thank you.
I was.
No, you're fine.
Okay, I see. Awesome.